Hello, everyone, and welcome to today's webinar. My name is Sonia Winkleman. I'm from the Canadian Home Builders Association, and I just wanted to give you a bit of information before we start with our presentation today. So I wanted to let you know because we have 250 people who registered for this webinar. We've got quite a few people, so we're going to have you in listen-only mode for the duration of the webinar, even through the question and answer section at the end. So if you do have any questions, please put them in the questions section of the dashboard, and I'll be able to ask those questions to Lisa at the end of her presentation. But I do want to note, again, because of how many people we have, we may not be able to get through all the questions, and so we can have Lisa respond to your questions afterwards via email as well. I did also want to let you know that we are recording this webinar, and we will be posting a link to the recording in the members section of the CHBA website after the call today. So probably in the next couple of days we'll get that posted. So if you do have any colleagues who missed it and would like to watch it, you'll be able to find it there. So today's webinar is called The Impact of Fenestration on the Building Envelope, a window of opportunity. The description of the webinar is about increasing energy performance requirements and codes means we need to rethink how we build envelopes, and we're examining the entire wall assembly, and optimizing the window specifications may prove to be the best opportunity for builders to cost effectively improve the overall performance of their homes. In this webinar, Lisa will show you how to select the right glass package to influence your cooling loads. She'll also show you that the window-to-wall ratio impacts the overall effective R value of your wall, and also that putting in better windows reduces the initial cost and operational costs as well. A more holistic approach to the building envelope may be the most cost-effective way to deliver high-performance homes, as well as increase comfort for the occupants. Understanding the energy performance numbers for windows and how they influence the size of the mechanical systems is key to providing cost-effective solutions to improving the building envelope. So Lisa Bergeron, who is the Government Relations Manager of JELD-WIN Canada, will be making this presentation today, and she is an Executive Board member of Fenestration Canada. She also chairs Fenestration Canada's Fabricators Council and has been a member of NRCan's Energy Efficient Fenestration Steering Committee, which dictates Energy Star fenestration criteria since its inception. She's also a voting member of the CSA A440 Technical Committee and is a sponsor member of the CHBA Net Zero Energy Housing Council. So without further ado, Lisa, feel free to start your presentation.
Okay, well, thank you. Good afternoon, everyone. Welcome to this webinar. I want to take this opportunity to thank CHBA for allowing us to do this, and thank you, Sonia, for thinking of us. We appreciate it. So today we're going to briefly review. Second, why is it not working? There we go. So we're going to briefly review who JELD-WIN is, what we do, and then how we got here from Super E to Net Zero. And we're going to talk about the study we did on the impact of fenestration on the building envelope, and how these results can guide your choices that you make as a builder. So who we are, I keep going back to this slide. This was done in the 2015 Avid Ratings Homebuyer Preference Survey. It was presented to CHBA members at the National Conference in Halifax. I like this because 5 of these 10 must-haves JELD-WIN manufactures and is able to provide builders with. We are the world's largest manufacturer of windows and doors, operating in 25 countries. We're a proud member of CHBA and the Net Zero Council, and we're also part of the Manufacturers Council. We make the widest range of products of any window and door manufacturer, from the $30 molded interior door panel to 30,000 plus folding wood and fiberglass door systems, to pretty much all window systems in between. We have the most diverse offering, catering to all needs and budgets. We provide security and beauty to the spaces that touch our lives. We strive to be good stewards of the environment. Our molded door skins, our interior door skins are NAF, non-added formaldehyde. We've been making energy efficient windows and doors that qualify and exceed the Energy Star criteria since 1998. We've recently participated in writing the first Canadian voluntary standard published last year for formaldehyde emissions and composite wood products. So we make a vast array of products, and we're very active in our industry. From a Canadian perspective, we're very well established in Canada. We're the only true coast-to-coast supplier of windows and doors, and we have a very large operational footprint covering all regions. So our path to this study actually started quite some time ago. Our journey is paved with partnerships with builders in production of high-performance homes since really the early 2000s. We were involved in large projects that were done in the UK with the Canadian manufactured home builders under the Canadian Super E program, which really was a sexy way of marketing our 2,000 homes abroad. These windows in these units didn't have triples. They were dual glazed low E argon, but they were very airtight. And these homes were actually running about 1.5 air changes an hour with 1.8 U values for windows and 0.45 solar heat gain coefficient. Then came our involvement with Energy Star and Energy Star for new homes, and the products now range from a 1.6 to a 1.4 U value with higher solar heat gain coefficient. In 2007, we participated in the building of the first Equilibrium House, CMHC Equilibrium House, the Eco Terra House in Eastman, Quebec. These windows were triple glazed, but they were not ideal triples. They were what we call skinny triples. They were only an inch total IG. So performance was better than a dual glaze, but it wasn't optimum performance for an IG unit. In 2013, actually 2011, we were approached by Team Ontario. So Carleton University, Queen's, and Algonquin College got together and participated in the DOE Solar Decathlon. We were asked to partner up with them. We were very proud and happy to oblige. And we supplied product that was between a 0.9 and 1.1 U value. So at these were now true triples that we had designed. We had redesigned our products, and we actually supplied product that had 3 low E's. So it was triple glazed product with surface 6 low E as well. In 2014, we partnered with Owens Corning in the NRCan Eco-II program that built 26 net zero homes across Canada. And in 2014, we became the founding sponsor of CHBA Net Zero Council. And now, along with Owens Corning and Detson, we sponsor net zero training for builders across Canada. So that kind of takes us of how our products and our expertise developed over a little while. I wanted to talk in 2011 was kind of a turning point for us. I was attending a BC Beck conference in Vancouver where John Straub from the University of Waterloo was speaking about energy efficiency and the future of building envelopes. It was really a fascinating lecture, but from a window perspective, it was also quite depressing. Windows, it appeared, were the weakest element of the building envelope, and they were the root cause of all evil. So this was not exactly motivating for someone in my line of work. But a few years later, again in BC, I was attending an NFRC, the National Fenestration Rating Council conference in Vancouver, and there was an energy simulator there that started talking to me about how we were not capitalizing on the opportunities that windows could bring to the building envelope. And in his mind, windows were the most cost-effective way to improve overall effective R value of the building envelope. So with this new information in tow, we began to take a look at what part windows played in the building envelope from an energy perspective and the impact that we could potentially have. So this brought us to take a look at a more holistic approach. You know, it's common knowledge that windows are the weakest link on the building envelope. There's no question about that. We're significantly less thermally resistant than an opaque wall assembly. But the story, is not about pitting one against the other. As building codes are becoming more stringent and energy efficiency becomes more important for consumers, we feel that we have a good story to tell. In a world where resources are finite, what's the best return for those resources? So, I believe it's in around 2012, there was an introduction of a more holistic approach to energy efficiency in new home construction. Instead of looking at the building as individual components, the alternative was to look at the house as a system approach. So a good way to illustrate this, this comes from the Canadian Wood Council, so thank you, Rob. And a good way to look at this is by looking at a wall assembly. Traditionally, this has been called an R22 wall because of the nominal value of the bad insulation, which in this case is R22. But the effective R value of the actual assembly is really 16. And when you put a window in it, then with an effective R value of 2.8, all bets are off. So to talk about the theory, we decided that the simplest way was to put together a building with 50% fenestration and 50% wall to show you the impact of fenestration and insulation on the overall effective R value of the wall. So in this particular case, you have 50% window-to-wall ratio, an R2 window, and an R20 wall. And so my effective R value of this assembly is 3.6. If I take the same building, and I improve the insulation in the wall, I double it, I really get just a marginal improvement in the overall effective R value. But if I take the same building and I double the effectiveness of my window, I get a pretty good bang for my buck. So this is what gave us to, got us to the point where, the biggest opportunity for us to improve the overall effective thermal resistance is to install better windows. But, theory is good, and we needed to study this further and study the potential impacts and benefits that could be had for builders, homeowners, and the environment. So we contacted CHBA and spoke to David Foster and Gary Sharp, and then Sonia and I and Andy Oding had a conversation, and we needed to transform this information into practical data that builders and homeowners could use. So we partnered with Building Knowledge and commissioned a study to analyze the impact of fenestration on the building envelope in relation to window-to-wall ratio. By looking at the windows as part of the building envelope and not an isolated component, and by going even further into the house as a system approach, it showed us that not only how windows impact the effective R value of the above-grade assembly, but how different glazings in new construction can influence operating costs for consumers, reduce greenhouse gas emissions, and reduce initial builder costs by right-sizing the mechanical. So what we wanted to know was really how a better window compared in relation to a better wall in an assembly, how the window-to-wall ratio impacted the overall above-grade assemblies. We wanted to know, were there any benefits for builders, and were there any benefits for homeowners? And so this got us thinking that we needed to look at window optimization, and we needed to look at window optimization for three major reasons: essentially occupant safety, occupant satisfaction, comfort, health, relative humidity, condensation, peace of mind, peace and quiet, energy efficiency, new codes, net zero and beyond, where were codes taking us, and then cost, to take a look at the first cost and the total cost. So the first element is thermal comfort, and thermal comfort is complex. We would need really a whole session on comfort, and it would certainly be given by someone much more qualified than I. But the major factors influencing thermal comfort are, ambient air temperature, surrounding surface temperatures, mean radiant temperatures, humidity, drafts, occupant activity. The best tool that we have available, which is a free tool, was developed by the Center for the Built Environment, and it's a tool that's made according to the ASHRAE 855 standard. It was made by, like I said, the Center for Built Environment at Berkeley. So I invite you to go see how different conditions impact the thermal comfort of the occupant. It's quite interesting. But from this tool, Cardinal Glass has extrapolated the following scenario for hours of discomfort that one would feel based on zone 6 and 7 at 1 meter from a patio door. And when you think about it, certainly in most homes, regular homes, you would have a dining room table or a kitchen table that would be somewhat positioned close to, about a meter or 3 to 4 feet from a patio door. So this is real life, a real life experience. So the first bit is would be like if you have a patio door with a metal frame and single glaze. Under the modeling tool, this would lead to about 3,000 hours. That's 125 days of discomfort in the wintertime and 300 hours of discomfort in the summer. If you take the same door and you just add a double glazed insulated unit in the door, so don't change the door per se, just the glazing, you come down to significantly to 500 hours of discomfort, which is still 21 days of discomfort, and then slightly less in the summer. But then if you take again that IG unit and you put it into triple low E, you then come down to 0 hours of discomfort for both winter and summer. And that's an important metric showing that, obviously the higher or the lower U value and more efficient tripanes actually do a lot to improve thermal comfort for the occupant. I'm going to go over this quickly. This shows how important the right humidity levels are on human health. So we spend a lot more time inside our homes and we produce a lot more moisture. Condensation is one of the leading warranty calls by builders across North America. And we know from the ASHRAE model that they recommend around 35% humidity in winter conditions. This graph simply shows how a tripane window 2 low E coatings is really better equipped to resist condensation at lower temperatures than a double pane and certainly than a single pane. So we're going to go into condensation resistance a little more later on. And although, thinking about putting in double pane and better U values, better U values don't necessarily translate into lower or higher condensation resistance numbers. So we'll talk about that shortly. We get to choosing the appropriate glazing, and before this may be known to everybody, but I thought it would be good to take a look at the anatomy of an IG. So an insulated glass unit. When we talk about IGs, we talk about them always the same way. So this shows a dual glaze and a tripane. We always talk about the surfaces going from the outside in. So in a dual glaze unit, you have surface 1, surface 2, 3, and 4. In a tripane, same thing, surfaces 1 to 4, and then you add 5 and 6. We have, in this case, these are warm edge indoor spacers from Cardinal. You have desiccant, you have also primary and secondary seals, and in between the two panes of glass, you have a gap that is filled with a mix of air and argon, or air and krypton. And usually it's 90% gas, 10% air. So low-E coatings are is essentially glass that's been coated with a low emittance material, usually silver. Multiple low-E's have unique characteristics. They increase thermal performance, they reduce UV rays, they reduce fading, they reduce heating and cooling costs. And you know, we have low-E 180 and 366 as standard options. We also have 272, kind of a medium solar gain. We have low-E 180 is designed more for passive solar gain applications, and low-E 366 is essentially for for solar control. I wanted to talk about U values and the numbers that define windows from an energy perspective. Thought it was important to make sure everybody understands. First of all, in some jurisdictions, namely Ontario and in British Columbia, every window that gets sold in the province needs to have a certified thermal rating, and the certification agencies are essentially, you can certify to A440.2 in Canada, or you can certify to also to NFRC, which the majority, I wouldn't say the majority, but a great number of manufacturers have turned to NFRC for their simulations, and certainly we have both, but we use NFRC a great deal. So I wanted to show you what the numbers that need to be on labels and in product literature should be on available to you as builders. So the U value measures thermal conductance through a product in watts per square meters. It doesn't take into consideration solar heat gain or air infiltration, exfiltration. The lower the number, the better. It measures total products, so be careful. Some manufacturers, some glass manufacturers, tout their center of glass numbers, and that's misleading. It's like the 22 bat thing. It's not a total number. And then resistance is a reciprocal of conductance. So in this particular unit, it has a U value of 0.97 or 1.17 in inch pound. The R value is therefore 6.88 for this particular unit. I wanted also to point out that something that's important on the NFRC labels is that you have to have the full CPD, which is the Certified Product Directory. Every glass configuration has for a window manufacturer has a CPD number, and so that full CPD number should be on the label. And if you go on, you Google NFRC, you'll find their certified product directory. You can search by full CPD number, and you'll be able to get the information, the complete information about this the IG unit that was simulated for this window. And so you have here the same data at the top that's on the label, so the U factor, the solar heat gain, the visible transmittance, and then you have the condensation resistance number. This is an optional, it's an optional measure. It's standard for NFRC, so everybody gets a condensation resistance number for their particular units, but it's optional to put it on the label. But you can know that you can always look it up on the CPD in the Certified Products Directory, and then it gives you the information on the glass. In this particular case, it's 2 low-E 180s. It gives you the gap width, spacers, and whether it's air or whether it's gas filled, whether there are grids, and whether the glass is tinted. So it gives you a lot more detail on the product. The next metric that's interesting, actually very interesting for builders and for looking at whole house energy modeling, is the solar heat gain coefficient number. It really is the ability for glass to absorb energy from the sun. So higher solar gain helps in heating dominated climates. It can lead to, it helps reduce energy consumption. It can lead to overheating. Low solar gain helps in cooling dominated climates. It does help reduce cooling loads. It blocks out more visible light, so it equals to a little bit darker. The solar heat gain coefficient affects about 50% of most heat load calculations. So this has this is really important on the tonnage and your calculations for your mechanicals. Another number is the ER, and that's the energy rating. It's developed in Canada, and it considers the U value, solar heat gain coefficient, and air infiltration and exfiltration. So it's a more complete number. It was meant to compare how much energy one window used versus another. It considers that windows absorb heat and helps diminish energy costs during the heating season. It was always meant for window-to-wall ratios, lower window-to-wall ratios. It can lead to overheating if this is the only thing you base your decision on is a higher ER, depending on the exposure and whether or not there's shading. It does lead to the lowest energy consumption models in gigajoules. And in 2013, I believe, we did a pan-Canadian study on energy, on the ER, whether or not it was still relevant, whether the calculation needed updating, and whether it was still a proven metric. And the results of the conclusion of the study, that was the study done by NRCan, by BC Housing, Fenestration Canada, BC Hydro-Quebec were all partners in this study, and the study showed that ER was still a valid metric and did still lead to the lowest energy consumption, but there was clear indications that it could lead to overheating with larger window-to-wall ratios and when you have southern or western exposure with no shading. And ER was not intended for MURBs. So condensation resistance. So in Canada, we do have, we don't measure, there's an optional condensation resistance, it's called a temperature index. It's optional in the standard. Not a lot of manufacturers go through that because it is very expensive and it's very time consuming. So, however, the NFRC has a metric that they track. As you saw in the earlier slide, it's called the CR, condensation resistance factor, and it measures how well a window resists to the formation of condensation on the inside surface. And it's expressed in a number between 1 and 100. So 1 being the higher the number, the better. The rating was based on surface given indoor surface temperatures at 30, 50, and 70%, and at an outside air temperature of 0 with a 15-mile-per-hour wind condition. Some people say that that's not necessarily the real world, or that it has flaws. It may have flaws, but at least every window in the NFRC database is evaluated under the same conditions. So in that sense, it is a fair number to compare one product when we want to compare their potential for condensation formation against another. as I said earlier, it is optional on the NFRC rating. And so this leads us to talk about window coatings and the effects on condensation resistance. So we've had a new phenomena that's about 2 years old, and essentially it's surface 4 Louis that's come a lot into play. We see it a lot more and more, and essentially that the popularity of surface 4 Louis came in with the new Energy Star criteria in 2015 that were NRCan moved up its criteria for Energy Star for windows, and so manufacturers were looking for ways to improve their U values without having necessarily to change the design of their systems. You know, those are expensive changes to make, and so manufacturers were trying to find glass that was going to help them get there. And so Surface 4 Louis has been in the U.S. Since about 2007, 2008, when DOE came out with their R5 program. And it's a valid, you know, in the U.S. it works really well, and this glass, as you'll see, does actually do what it says it's supposed to do, which is reduce the U value. So when we were talking about surfaces on the earlier slide, this actually shows these are actual numbers out of the NFRC database that we took and we put into a format that is easily importing, that you can input into HOT 2000 files. So just to give you a brief rundown, you have here the U, the center of glass, the edge, the frame, and the total U value. So this is the number that's on the label. This is the number that's in that should be in product literature. Then you have your solar heat gain, again, center of glass and total, and then you have the ER and the condensation resistance. So the first item here is clear. So this unit, actually, I can't even sell in Canada anymore for residential construction. You need low E now pretty much everywhere. But this particular configuration, which is the base, a clear air clear, is at 2.27 U value. And condensation resistance number of 46. When you add a low E coating on this, in this particular case, it's a surface 2 low E, and you fill the airspace with argon, you can see that you have a very big impact on the U value. So you go from a 2.27 to under 1.5, and you increase your condensation resistance number. Remember, the higher the number, the better for this in this unit. Now you come to the third item where you have low E. You have two low E's, so you have a surface 2 and a surface 4 low E. And again, this actually does what it's supposed to do. It reduces the U value, so it significantly reduces the thermal conductance of the product. But by doing so, it also reduces the surface temperature of the glass and brings the condensation resistance back down to almost that of a clear. So the moral of the story is be careful when you get good U values on dual glazed units. They may have surface 4 low E. Under certain conditions, surface 4 low E works fine. We recommend it for zones 4 and lower. We actually have products that are simulated and we offer surface 4 low E. So it's not the root cause of all evil, but it depends on where you install it. You need to be cognizant that this could be a problem. So you know, ask for condensation resistance. This is this picture shows in the same window, one side, the right side being surface 4 low-E and the left side being just a regular surface 2 low-E. And you can see that there's significantly more condensation under the same conditions on the surface 4 low-E. So just know that you could be exposed to that. I guess in parting, talking about the numbers, just be careful that you're not considering just one factor, that you're considering all factors when you're choosing your windows. You know, the lower the U value, the better, but consider choosing the appropriate solar heat gain to avoid overheating. And in many cases, tri-panes actually solve a lot of these problems that are linked to dual glazed units. So, what we know about windows, you know, the amount of glass is definitely growing in houses. When we look at the 2000 or before, it was 8 to 10. Between 2010 and 2016, they grew from 12 to 17, and now you know, you're seeing products 17 to 25. So more bigger and more and bigger windows and more electrical appliances mean more air conditioning, but more air conditioning also changes the way our houses work. So we used to worry about heat and moisture flowing out. Now we have to worry about heat and moisture flowing in. So when we talk about air conditioning, it is the fastest growing peak load. We have it's the most costly electrical use in Canadian homes. And the heat load is determined primarily by windows. So 50% of the cooling loads is determined by glass. And the duct size is determined, is determined by the cooling loads. So not the heating loads in most new energy efficient homes. So this takes us to our study and what we wanted to review for, and we wanted to study with regards to windows and the building envelope. What we used the Hot 2000 program. We did about 1,400 simulations. Our base wall was a 2x6 wall with 22 batt. We used dual glazed high solar gain low-E windows kind of as our baseline. We used local utility costs and we used climate zones 5, 6, and 7A, which is the bulk of the population in Canada. We used our study analyzed 4 building types. We studied two-story detached, two-story single detached, bungalow single detached, townhouse, and a mid-unit and an end unit in a townhouse. We studied 6 window-to-wall ratios, 8 window models, dual glazed high solar gain and low solar gain, triple glazed high solar gain and low solar gain in both the plants that we're manufacturing in the east and the west to cover the entire country. We studied 4 above grade wall configurations. So we studied the base wall was the R22, 2x6 R22. We studied then the we did an R20 with an R5 batt. Continuous insulation on the exterior, an R20 with an R10, so a 2-inch on the exterior, and then we also did a 2x6 with an R24 batt, which is a wall that's more commonly found in central Canada. So these whole configurations resulted in about 1,400 Hot 2000 files. So the conclusion of the study were, bang on to our theory that windows really do have a great impact on the building envelope. So these 2 lines represent the effective R value of the above grade building assembly. The dotted line is the house insulated with R 22 bad and a Geldwin triple glazed window. The dashed line is house insulated with R20 plus R5 continuous insulation, and then a Geldwin double glazed window. So as the window to wall ratio increases, or as we move from left to right along the graph, the window becomes more important to the overall effective R value than the solid wall portion. So in the study, we concluded that for all three climate zones, beyond 13% window to wall ratio, a higher effective R value is achieved with a triple glazing rather than an R5 insulated sheathing. We did this same graph showing an R10, so it's the difference between a triple glazed and an R10, and the tipping point becomes 20% at that point. So, taking advantages of growing window-to-wall ratios, the greater one of the study conclusions was obviously the greater the window-to-wall ratio, the more important choosing the right window becomes. For all homes, so all types of homes in Zone 5 and 6 above 12.5, tri-panes were better than using an R20 with an R5 insulation on the exterior. In all homes for Zone 5 and 6, above 20% window-to-wall ratio, tri-panes were improved the above-grade effective R values more than using an R10 exterior insulation. One thing that we didn't expect was that low solar gain glass reduces air conditioning loads by up to 50%, between 1 to 1.5 tons. So some significant changes there depending on the configuration and the window to wall ratio. And then tri-panes do improve the R value of the envelope at 15% by 16, at 15% window to wall ratio by 16%, at 20% window to wall ratio by 22, and then 25 window to wall ratio, an improvement of 24%. One thing that I forgot to mention is when we did talk to builders, we talked to building knowledge about doing the study. We wanted to do a builder roundtable because all this data really means nothing if it can't be translated into something meaningful for builders. So in August 2015, we did a builder roundtable with this study. Essentially, they were in the Greater Toronto area, builders of ours in the Greater Toronto area. The feedback that we got were that builders were facing really aggressive building codes, new volunteer program targets, and optional incentive programs. They had heard that windows were becoming important, but weren't too sure. Nobody was taking the lead. They found the report useful. They liked seeing the key conclusions. They found that pricing estimates were in line and accurate, so we had done some case studies to show the actual savings that could be had. They recommended that we start comparing the 1-inch and 2-inch of foam, and that this was a critical decision point for builders as they assess new codes and the Energy Star programs. They noted that tri-panes were less money than they expected. And they also liked that there was a possibility of decreasing AC equipment costs and operational costs through optimizing the solar heat gain coefficient. So this led to the opportunities checklist for them. Homeowners, our expectations are rising. That's that's just a regular matter of fact, the sign of our times. Energy codes are advancing. The total cost for them was a better metric than the first cost. Window areas are increasing. AC is now becoming normal in most new homes. Humidity levels need to be maintained for occupant health and comfort, and they felt they needed to select knowledgeable manufacturer partners. So the challenge for us was translating all this knowledge into value for our staff, value for builders, and value for homeowners. As you can imagine, 1,400 energy models creates a lot of data. The challenge was to translate the data into tangible elements that our staff could present to their customers and builders and homeowners. So we developed a tool, an envelope optimization tool. So this is not a public tool. This is not even available readily to our customers. This is our staff, so our inside and external salespeople have been trained on this tool. They understand the fundamentals of building science, and they're able to essentially take the data that we did from our HOT 2000 simulations, and this tool is meant to be able to compare, so to help a builder make decisions. It's not, this doesn't replace energy modeling. This is a snapshot in time for a particular case in time. So, but this I like the way Andy Oding says this is will give you direction. It helps, you know, if you're on a 10-story building and it's on fire and you need to jump off, this will at least tell you which side of the building the pool is on, so you have a fair shot of jumping. You have a fair shot at surviving. So what I wanted to show here was a couple of examples of how, with the data that we've gathered, we're able to analyze or compare essentially two different configurations within our database. So here we have, what we're doing is just comparing a tri-pane window with a minimum code window, so the dual glazed high solar gain. So in these two simulations, or the results of these two simulations, show us that, you know, for a single detached 2-story home at 15% window-to-wall ratio in Zone 6, you know, the wall configurations are the same, but here you have a tri-pane low solar gain, and here you have a dual glazed high solar gain. You take a look at the effective R values. Well, the tri-pane one obviously gives you a better overall effective R value. It also lowers the energy costs by almost $300. Decreases the greenhouse gas emissions by about half a ton. And drops the BTUs for the cooling by about half a ton, by over half a ton. So this is the impact of just switching out on a regular build windows, tri-pane windows for against a regular dual glazed unit. When we compare the better window versus a better wall, we have a different story. This is this one is in Zone 7A, so this would be Calgary. For example, in North, Winnipeg would be in this as well. We had single detached 20% window-to-wall ratio. Here we have a better window in a regular wall, and here we have a better wall and a regular window. And you can, as you can see, we have in the better window, we have a better effective R value. We have lower energy costs here, about almost $300 again. We have almost 1 ton of greenhouse gas emissions, and we've dropped our tonnage per cooling load by a ton. So, you know, what does this mean for builders? You know, better windows versus better walls. You know, a better window means a PO change, no learning curve. You know, it's the same to install a dual glaze than a tri-pane. We're reducing callbacks, and that means savings. We're reducing the risk of condensation. We're increasing occupant comfort. They're quieter, so the homes, as homes especially, are more efficient. This helps, and it reduces the mechanical side, so that's additional savings for builders. for when you have to go to a better wall, there is a learning curve. It's additional labor. You have to think potentially of thicker foundations. That's all more money. There's mechanical systems and consumer discomfort, and increased callbacks because of condensation and discomfort when you're next to the window. So the conclusions for us is, if you haven't looked at triples lately, as a builder, you need to. If you need help on how to improve your customer comfort levels, and if you want to help reduce your callbacks, then let's have a conversation. So with that brings my presentation to the end. Do you have any questions, Sonia, for me?
Thank you so much, Lisa. That was a great presentation. And we do have one question that's come in so far. So I'd like to take this opportunity to remind everyone that if you have any questions for Lisa, please put them in the questions section of the dashboard, and then I can read them out to Lisa. I was just going to ask you, Lisa, if you can also put up your contact information so that they can get a hold of you directly too. So that's great. Thanks for putting that up. So okay. Niels has a question here. He's saying that there is no size of window which resulted in the U values on the label. Without this, how do we calculate the actual U value for all the different sizes in a house?
Well, I think that's with the, if I go back to the data needs to be in the file that, sorry, hope I'm not making anybody dizzy, but in this format, I believe that if if your manufacturer is sending you data in the input file in this manner, you're able to right size the windows as per the building. I can validate that, Sonia, and you're obviously noting it, and so we can I can make sure that that's the case. But that's what I'm being told. I'm not a simulator, but I'm being told from our energy modelers that this format will allow you to do that.
Okay, perfect, great. So Niels, if you want some further information on that, we can also connect you with Andy Oetting, who did the study, so he could explain it a little further as well. And that actually might be something I believe we're going to take a look at putting into the Net Zero Energy Advisor training. So that would be a helpful calculation, and Andy has also been a part of putting the content for that Net Zero EA training together.
Okay.
So Veronica wanted to know if your study is publicly available.
It is not. We've, you know, that's something that we need to consider. We've been working on things like our tool for the longest time, and we spent actually quite a bit of money on this research and developing the tool. So we're still being quite I was going to say self-centered, but yes, I'm sorry, I'm French, so I'm trying to search for my word, but essentially we have not made it public yet. We have certain people have at it. NRCan has it because we have a confidentiality agreement with them, and several other educational and certain other groups do have it as well, again with confidentiality agreements. So you know, hopefully we'll publish it one day, but right now we're still trying to make sure that we have the advantage because we did spend a lot of money doing this.
Okay, thank you. And we've had a couple of people ask for copies of the presentation. So for those of you who missed that at the beginning when we opened the webinar, we will be making a copy of Lisa's slide deck, as well as a link to the webinar recording available on the member section of the CHBA website. And if you do need to get linked into that, please feel free to send me an email and I can let you know how to best do that. There was also a question from Bill asking, were the results for Zone 4 also positive for triple glazed windows?
We did not do climate zone 4, so I would I don't want to this, I don't want to misspeak. We would have to do you know, I mean, there are things that, from an energy perspective, my guess would be it would obviously be less of an impact because you've got lower, lower heating degree day in that zone. However, you know, occupant comfort and resistance to condensation and quieter, all those other factors would definitely still be winning combinations. So zone 4, we didn't do zone 4. We know that obviously the further south you go, the energy portion is not as important. Certainly from improving the above grade wall assembly, it would still hold true, but not necessarily from a energy cost or energy consumption. The difference wouldn't be as great.
Okay, thank you. We've got a few more questions that have been coming in here. So Stephen is asking, is JELD-WEN working on a frame that has a better U value?
We're yes and no. We have we're always working on different different systems. I would say that, you know, we have JELD-WEN R&Ds in Klamath Falls, Oregon. We have a lab where we do everything from impact testing to IGU testing, materials testing. So we do a lot of that as well as the structural testing. So right now, in the short term, we don't have a new frame coming out in Canada per se. That doesn't mean that we don't have anything in the U.S. And, you know, we have, I think that's a more specific question. If that person can maybe contact me directly, I can maybe try to find out, because we have many frames and many, you know, in many different locations. So
Okay.
I think that would probably be
I can connect you to for sure.
Okay.
The next person is asking, how does the JELD-WEN frame handle the extra weight of the third glazing? Is it built stronger than a double glazed frame for this purpose?
Yes. Essentially, our windows were designed to hold tri-panes, and that's why I found it interesting, or I felt I needed to show the evolution of how we went from, in 2007 at the CMHC Equilibrium house, where we were essentially trying to jam pack a tri-pane into a regular dual glazed IG unit, and we were doing what they call skinny triple. And so those windows were not necessarily designed to hold the extra weight. In our case, we obviously did the calculations because we wouldn't want to sell something that wouldn't stand the test of time. But the window was not designed to hold fundamentally at its base to hold tri-panes. And so that's why when we looked in time to the 2011, when we started working with DOE, the Team Ontario for the DOE project, then we had at that point developed true tri-pane expertise. And so the frames and the sashes are designed to be able to hold the extra weight of the glass, and the hardware is calculated to hold the extra weight of the glass as well.
Okay, great. Natalie's asking, what is the upfront percentage cost of a triple pane with the coatings versus a minimum code window?
Well, that's a hard one to say because glass is, you know, we would say anywhere between 10 to 15%, and that's really very loose, because going from dual glaze to tri-pane affects one section of the window. When you talk about, you know, it depends on whether the window is painted. So in relation to one another, the upgrade for tri-pane can be very small if you have a lot of accessories on the window, and it can be at worst case scenario, like I said, between 10 to 15%. when you're looking at just a regular plain Jane white vinyl window.
Okay, we only have 1 minute left, so I'm going to ask one more question. This one is in regard to how would very low solar gain windows perform in older homes, and how much would their energy costs be reduced? I think that's a tough one to answer as well.
Yeah, I think that's a very tough one. We'd have to take some looks at modeling. We have not, for renovation, we haven't even looked at the potential. We really haven't, because there are so many factors that impact a renovation. You know, are you redoing just the windows? Are you redoing the windows and, you know, insulation? Are you redoing? Is there a cooling in the house? So for me, that's too complex to answer. You know, I don't feel I have the capabilities or the competency to answer that without taking a look, you know, and running it through an energy advisor.
Okay, great. Well, this is where we have to wrap up. It's 2:30. There are still many other questions that we were not able to answer. So for those of you who are still on the line, I will work with Lisa to get you the answers to the questions that you have. And again, if you wanted to watch the webinar after, that will be available. I'd also like to invite you to participate in our February webinar coming up on February 16th from 1:30 to 2:30. It's called Tools to Help Design Building Envelopes for Net Zero Homes. And we invite you to join us for this webinar to learn about some of the tools that energy advisors and builders are using to help design building envelopes for net zero homes. Each of the 3 presenters will be, possibly 4 presenters, will be providing an introduction to their tool, highlighting the key functionality and outputs. You'll learn where to access the tools and who to contact for more information, and of course, as always, have an opportunity to ask questions to the panel later. So we'll be having Sal Charlo from Owens Corning's present on their thermal project calculator, as well as Rob Jonkman from the Canadian Wood Council present on their wood wall thermal design calculator, and Patrick Ropel from Morrison Hirschfield will be presenting on their thermal envelope guidelines. And if we're lucky, we'll also have someone from Enercan presenting on how to do appropriate solar design using HOT 2000, so that you can figure out what your electric budget is before you finalize your envelope design. So I'd like to thank Lisa very much so for this fantastic presentation. We've had a lot of other people comment that they really enjoyed the webinar. And so thank you so much for giving us all this wonderful information, and we'd like to therefore close off the webinar. So thank you everyone for coming.
Okay, thank you. Goodbye.
Have a great day, everyone. Bye-bye.
Bye-bye.